Hello guys, I'm a teacher Limboka Nsajika Masame. Welcome to Limboka Physics. We have a question below, question number 8 from Thai. States that a 15 kilogram object and a 10 kilogram object are suspended joined by a cord that passes over a pulley with a radius of 10 centimeter and a mass of 3 kilogram, as shown from the figure below. The cord has a negligible mass and does not slip on the pulley. The pulley rotates on its axis without friction. The object starts from rest 3 meters apart. Treat the pulley as a uniform disk and determine the speed of the two objects as they pass each other. Okay, in order to attempt these questions, let us consider the diagrams below. We'll use this question just to take a look on 3 cases. The first case is when one object it is above 3 meters from the floor, as you can see here. Well, the second case is when both of these two hung objects are in the same positions in a horizontal level. For the first case, let us consider the freeboard diagrams and the diagrams also with vectors. A body diagram with vector. Okay. This is the center of mass for the M2 and the center of mass for M1, and this is our circular disk, a uniform circular disk, act as a pulley. And the tension acting in mass 2, as you can see here, the tension 2 is moving up and the weight down, and the tension 2 that is moving through the direction of the weight, it is in red color, and it provide a necessary torque that is in clockwise direction. While in mass 1, the tension T1 counterbalanced by the weight of mass 1, and its respective tension that is directed towards the direction of the weight is responsible to provide a torque which is moving this pulley, this disk, in anti-clockwise directions through the center C here. Okay, this is a displacement through this arc, displaced as angular displacement stripe as the strings pass through this pulley, moving in directions, and this is net torque and angular velocity, which is final angular velocity. We'll have final angular velocity. For the position case, for first case, the mass 1 is at a coordinate of 0, positive s, while the mass 2 is at a coordinate of 0, 0, and this is final condition state for mass 2, and this is also final condition for the state of mass 1, while the first condition, the initial condition, it is when the mass 1 is at coordinate 0, 0, while mass 2 is above the floor 3 meters. Okay, let us consider the uses of Newton's second laws of motion, of linear motions. By considering Newton's second law of linear motions, we consider net force that is equal to sum of forces in y direction. We don't have x direction here. Okay, for y directions, as you can see here, for mass 2, as you can see, for mass 2, body of mass 2, weight is moving down negative and tension 2 is in positive, then our net accelerations is always down. It is in clockwise direction for the pulley, and for the linear motion it is moving towards negative y-axis. While for body 1, mass 1, as you can see here, the freeboard diagrams, T1 is in positive as usual, weight is negative, and acceleration here is moving in positive y directions. It is positive also. We have 2 equations now. After forming these 2 equations, let us add these 2 equations and see what we'll have. We will have the equations after adding, as you can see here below. And then let us just do a simple mathematics by removing this negative from acceleration A in each side and rearranging the equations. After rearranging the equation, you can see the equation as arranged as in this way. Then let us consider the case for the torque. We consider the second Newton laws of rotation motion. The net torque is equal to sum of torque that act on the disk or the pulley through the center. For clockwise and anti-clockwise, consider T1 times R, it is in anti-clockwise, while T2 times R, it is in clockwise directions. Therefore, we know that our net torque is equal to moment of inertia through the center, angular acceleration net. It is also in negative because it is moving in negative directions. Therefore, if we substitute as angular acceleration as negative, then we have this result for the expression for the Newton second law for rotation motion. Okay, when we substitute by dividing, make the subject this net torque to the rest of the right terms, then we substitute this net torque with the rest of the right terms, then we will have the equation as you can see here below, after multiplying this r in both sides and this moment of inertia passing through the center. Okay, let us go directly to the continuations of this equation here below. Then here we just define the linear accelerations as r times angular accelerations, and then we are supposed to make the subject for angular acceleration here. After doing the mathematics, we take brackets out and we make the subject the angular accelerations. And from the third linear equations of motions, as you can see here, then we substitute directly the linear acceleration to angular accelerations, and we are in position to find the velocity v is the final velocity. The final velocity will be expressed as you can see here as the root of these equations inside, and then after getting this general formula for linear velocity of the system, then we substitute the data and we will have 3.36452, approximately 3.36 meter per second. This is for the first case by using the Newton's second law of motion. Thank you for watching. Please like, share, comment. Don't forget to subscribe to this YouTube channel for more videos like this one. Wait for the second case when we use the conservation of principle of conservation of energy, and for the case when the two masses are on the same level. Thank you.